can't get this to stop playing. Hello and welcome to your Chapter 5 notes. I am currently upstairs hiding from all of my pets because they make noise, but you're probably still going to hear at least some of them on this video despite me using a microphone because, well, anytime I make sound, they feel like they need to answer me because flock calling is what birds do. They want to know where their family is. So that's where it's at, yo. They're just trying to figure out where I am because they can't see me, which is kind of funny. Anyway, so the goal today is to just get through some of chapter 5 so that we're not behind, and that's about it. So we're going to do this little video times right here, and then we are going to have a little assignment to do afterward. That's about it. Let's get this party started. So we've been dealing with probability up until this point and talking about the likelihood of things happening. So now we're going to combine that with the idea of keeping track of what are called random variables. Now, if you remember, we did talk about random variables at the beginning of the probability chapter on chapter 4 about that a little bit. And I mentioned some things, but I didn't quite get into a whole lot of details. We'll do a little more details first, and then we'll get into some of the math behind this. And then and that'll be about it. That's about as far as I'm going to get today. So hopefully this will be short and sweet, and it'll be a good time. So first off, I have to tell you what a random variable is. So a random variable just simply takes on different numerical values based on chance. So you don't know ahead of time what the value of the variable is going to be. Come on, you. That's way too thick. Eraser. I like this app right about until now. So it takes on different numerical values based on chance. So be thinking, I don't know ahead of time what the answer is going to be or what the outcome of this event is going to be. So we talked about, random events and random sample spaces and stuff. So hopefully you see the connection here. So we're going to look at two different types of random variables, discrete and continuous. So discrete are going to be the ones that can only assume a finite number of values or an infinite sequence. So in case you forgot, like an infinite sequence is things like 0, 1, 2, 3, and then just continues on forever. So it has to all look the same and be a sequence. And then the continuous ones are just going to be anything that looks like infinity. So it has an uncountable number of values. It's got so many possibilities you can't count it. And that's what uncountable means. So be thinking, oh, no, I didn't hit that. Infinity. So I'm going to do some example of these to help you out. But the idea is that no, good God, I'm having all kinds of problems with this. My touchscreen's a little too sensitive today. Basically, the idea is this one, discrete, feels like it's not infinity, and then the other one will feel like infinity. In fact, finite is just, infinity without the in. The in actually means not, so not finite, can't count it. And then discrete will be the stuff you can count. So we're going to be focusing in chapter 5 on only the discrete stuff. We're going to do some continuous stuff, but not all the continuous stuff when we hit chapter 6. So let's get an idea of how to recognize something being discrete or continuous. So there's an example. Suppose we're going to look at some random variables. We're going to ask ourselves, does this feel like it's discrete or does it feel like it's continuous? That is not what I expected that to do. again, I want the eraser. Jesus, the number of things I'm going to have to like cut out of this video is going to be extreme. Anyway, yeah. So suppose Y is the number of drop calls experienced per day by a customer in a particular cell phone carrier. So I'm hoping you look at this and you think, okay, number of calls. That's something I can count definitely. And it's probably not infinity because although it might feel like you're waiting forever to get a call to work, that just means you have a bad carrier. But you can only lose so many in a day. So this is probably going to be something you can count, and that's going to make it discrete. Discrete is Latin for to cut. Fun fact. So you can cut it up into whole pieces is another way to think about it. So let Y be the time it takes the technical support staff to complete troubleshooting a service call. How long is it going to take before we get power back is another way you can think of this. So it's amount of time you're waiting. The big thing about time is because you have no idea how long it might be, and you also have so many different ways of measuring it. You could be doing minutes, you could be doing half minutes, you could do hours, you can do whole days, you can do long, long, long periods of time. And it's got so many options there that this feels like infinity. So we're going to call this continuous. Continuous is hard to spell. Got lots of U's. Okay, let X be the MPG rating of a particular model of car. So here we have to be careful. You can, and how you used to do this back in the day is you keep track of your mileage and you keep track of how much you fill when you fill your tank, and then take the difference and divide them to get your actual miles per gallon. Now, a lot of modern cars will calculate this as you drive, which is kind of cool, but it's an estimate. The one thing you want to be careful about with this is as you look at it, MPG rating. The rating is usually what's reported by the manufacturer. Since that's what we're looking at, it's usually only to like one decimal place. So since I can count that, this is going to feel more discrete. And you also know a reasonable range for what this should be. It's somewhere between 0 and like, I don't know, 100, because I don't know a single car that's over 100 miles a gallon at this point, but I'm sure this will change over time. Also, when we let go of gas, that'll be something different. Anyway, so this feels discrete because of how it's being reported. However, if you're looking at the cars that automatically report their miles per gallon as they're being driven, those values, well, they can constantly be in flux and change. I would say that feels more continuous. But because we're going with the rating the manufacturer produces, this is going to feel discrete. All right. This is supposed to be funny. Let X be the number of times you open your book during the semester. Yay! Now, for a lot of you, I'm assuming you bought the ebooks. There's no physical book for you to open. Because of that, this is going to feel. I'm going to adjust my mic. Doot, doot, doot. This is going to be 0 because you never actually physically opened it. But the point is, you can open your book a number of times, many, many times, but probably not an infinite number of times. And you also can't partially, well, you could partially open a book, but it won't do you any good. So we're going to call this discrete because I can count how many times I have opened the book. All right. From what we've learned about time, your guess for E should be very, very easy. Let X be the number of hours you study for an exam. So I know it says hours, but you can also study partial hours, right? Maybe you studied 3.7 hours. Maybe you studied 2.66666. That was scary. Hours. So the point is, you have so many options for this one that it's going to feel like infinity. It's going to be continuous because of that. One little pro tip for you. Hey, we generally always treat time as continuous. And we'll also do the same for distances just because there's so many options when you're moving or changing something. All right, let's talk about discrete specifically. So there's two very common types of discrete random variables that we're going to be looking at. And the first type is simply the ones that have many, many, many possible outcomes. So we've seen a couple of these already, but just to get you some more, how about like number of rings before you answer a phone? Woohoo! Because we all answer phone calls nowadays, right? No one does. Because you can count it. And then the other really common thing is stuff that only has two possibilities. And this is going to be something we spend more time on because, in general, when we're looking at statistics, usually there's some characteristic in your population that you're going to want to track. I want to know, do they have this or not? And then how many of them have it? So that's going to be something we spend more time on going forward in the rest of this chapter. So some typical things for this would be like any type of yes or no question. Woohoo. Um, a game result, like maybe you want to know, did you win or lose? Tying is for, you know, if you tie, you really lost, right? Everybody loses. Oh, I'm sure I'm going to hear about that. Um, and then, like I said, any characteristic you want to track. So maybe I want to track the number of people in my population that have a college degree. You either have one or you don't. So it's a two option scenario. So So, funnily enough, characteristic tracking is what I did my master's degree in. So, keeping track of whether or not certain groups have certain characteristics. And yes, it is an area still studied today. So, you are now getting into the era of modern mathematics, even though that was about 10 years ago. It's still something that people use. Anyway, so let's look at an example. So I've got a real estate company here in La Quinta, California, that shows homes with various numbers of bedrooms, and then they keep track of number of bedrooms a house can have, and then the probability they have for relative frequency of occurrence. So they've been keeping track of their home sales and what size houses different homes have, and then this produces a distribution for them. So you'll notice that, like, oh, it looks like, you know, 2 and 3 bedrooms are the most common because they've got the highest probability. And then 1 and 4 bedrooms, they kind of have the same likelihood, and then 5 bedrooms being the smallest. So notice we're doing this in probability, not percentages, because you can't calculate anything with percentages. But for some reason, when we write things out, we'll say things like there's a 40% chance of someone having a 4 bedroom home if they're, sorry, a 3 bedroom home if they list their home in La Quinta, California. So that's kind of fun. So what I want you to take from this is previously when we've looked at doing stuff like, oh, well, what's the average number of bedrooms a home might have? What you would do is you just like add up all these guys and then divide by, well, there's 6 of them, 6 and stuff. And that would work great if the number of bedrooms was all equally likely, but they're not. Clearly, 2 and 3 bedroom homes are more likely to happen because they have a higher probability. So what you want to look out for here is those should have more weight. They should be they should have bigger effect. Our average should be closer to 1 and 2 bedroom homes. So you might ask yourself, how can I do that? Well, the answer is to use your probability to affect how often or how much each of these values shows up. So we get a different formula for how to calculate the mean and how to calculate the standard deviation. Do, do, do. All right. So instead of calling it just the mean, we call it the expected value because it's the value you expect to get on average. Value you expect on average. And don't fool yourself, this is the mean. It's not anything scary. It is exactly what it's supposed to be. Okay? No crazy times. I'm going to make my pen a little thinner because I'm a little worried this is going to be too thick when I write it. There we go. So we write this as the mean is the expected value of the variable x, which is the same as I'm going to add up. That's supposed to be a sum sign. Regret. The product of the values for x times their probability. I'm going to do some of these, so if this formula looks scary to you, it's not as bad as it seems, but if you remember back to doing means by hand, it's very similar. Notice there's no dividing because everything's being affected by its probability size, not by how many there are. And then the standard deviation also changes. So we write this a couple different ways. I'm going to probably just use the sigma notation for it, but you might see people write, oh, well, this is the standard deviation of the random variable x, just because you might have more than one random variable floating around, and it helps you keep track of which one you're actually doing. So this one involves a square root, don't think this is anything different from what you've already seen. If you remember, in order to get to our standard deviation by hand previously, we also had to square root some stuff after doing a bunch of squares. The sum, again, my sigmas are just terrible today, of, here we go, how far x is from the mean, yeah, squared, does that look familiar? Times the probability this time. So again, you're not adding them all up and dividing by stuff because that assumes everything's equally likely. Instead, what we're doing is we're using probability to decide how likely something is. So let's return to our La Quinta example. And I keep saying that weird, and I probably should apologize for that. And what I'm going to do is I'm going to calculate the mean. And I've got some stray marks here. And then after that, I'm going to calculate the standard deviation. So what I need to do, looking back at the formula up here, I need to figure out what x times p of x is and then add them all up. So for this space I've got here, I'm going to do x times p of x. So for this first row, x is 1 and its probability is 0.1. So I'm going to do 1 times 0.1, which will just give me 0.1 back. For this next row, I got 2 times 0.3, which will give me 0.6. And this next row, I have 3 times 0.4, which will give me a 1.2. So you notice already that 2 and 3, because they're more probable, are having a bigger effect because they're multiplied by their probability. I got to do 4 times 0.1, which will give me a 0.4. And then 5 and 6 are both times 0.05. I'm trying to make these fit. Why am I yelling? Good times. I should have zoomed in more. This comes out 0.25 and 0.3. Sorry, I'm missing a 0 in here. There we go. Sorry about that. I was just doing half, which isn't true. It's half and then 1 decimal place over. Anyway, so then you add up all these values, and that will give you your mu, which is the same as the expected value of x. So you'll take the 0.1 plus the 0.6 plus the 1.2 plus the 1.2 plus the 0.4 plus these 0.0. Anyway, when you do that, you get 2.85, which makes sense. On average, a home in La Quinta, California will have 2.85 bedrooms. This is a long run average. Keep in mind, your average does not have to be an element in your data set. Typically, it'll have 2 to 3 bedrooms if you want to think about it that way. Or every, if I look at the average across 10 homes, they should have 28.5 bedrooms because that's normal to think about. Self-judgment increasing. All right, let's erase my little snaggletooth. Okay, so to do the next part, there's actually quite a bit I have to do. So looking back at the standard deviation formula, I'm going to work from my inside out. I'm going to subtract the mean from everyone of x, and then I'm going to square it, then I'm going to multiply the probability of x, then I'm going to add them all up. So there's a lot that's going to happen, okay? The first thing I need to do is do some subtraction. So I'm going to do x minus the expected value of x, which the expected value of x I just calculated. It's at 2.85. So I'm going to do 1 minus 2.85. I'm going to get negative 1.85. I'm going to have a hard time getting these to fit. I got to do 2 minus 2.85, and then 3 minus 2.85, and then 4 minus 2.85, and then 5 minus 2.85, and then 6 minus 2.85. And I know what you're thinking. She's going to let us use Minitab to do this. Minitab won't do this. Well, I mean, you can kind of make it, but you have to be like careful. I would actually advocate using Excel to do this. Anyway, so if you do these subtractions, you'll get negative 0.85 for this one, and then 0.15. That's the first one that's going to come out positive, and then 1.15. I'm calculating these as I go. 2.15, and then 3.15. Cool. So that was the first step. Now I got to take that and I got to square it. So this is pretty easy because all I have to do is take my previous row and then square it. So I'm squaring negative 1.85 and getting 3.4225. Now these I did ahead of time because I wanted to be careful. So I'm going to take negative 0.85 and square it and get 0.7225. Be careful with this. I know the temptation is to round, but when you round, you introduce error, and if you're doing it on every calculation, this can get out of control really quickly, and you can end up with some really inaccurate information. 0.0225. Oh yeah, that's the tiny one. 1.3225. and then 4.6225. And 9. Oh, that should be the big one, 0.9225. Because it's like 3 and 3 squares is 9, so it should be a little bit bigger than that because of the 0.15. All right, almost done. So many things. So I just did this part. I did the squaring. So now I'm going to multiply it by the probabilities. So I'm going to take this column and multiply it by the probability column. So for this first one, I should write out what I'm doing. So I'm going to take 3.4225 times 0.1, and that will give me 0.342. I get to take 0.7225 times 0.3, and that will give me 0.217, and so on and so forth. So I'm going to just write these out because I believe in my heart of hearts you can figure this out at this stage. You see the pattern, everything's okay. However, if you're somebody who's going to watch this video with the sound off, I'm very concerned about your ability to understand what's going on. All right, there we go. So that's all of that. So then what I got to do is I got to do the sum of this column. So you're going to add all these guys up. When you do that, you get 1.427. I encourage you to pause the video and double check that you get this when you calculate it, just to convince yourself you do know what you're doing. And then the last thing is that the standard deviation, I said I was going to use sigma for this, and then I'm going to proceed to not do that because I'm awesome, is just the square root of that sum, 1.427, which when you do that square root, you get 1.195. Okay, I'm having... Alrighty, so again, last steps, add them all and then take the square root. Good times. Let's do another example of this. I'm going to roll up. Getting tired of the blue. Let's try a different color. How about some purple? Ooh, that's a pretty purple. Okay, so we're going to play a game. Suppose you're given a chance to play a $3 game in which you win. Sorry, you have to pay $3 to play a game in which you roll a six-sided dice and then you receive a payout of $1 times the value upon the dice. What's your expected profit for this game? So this is going to be a little complicated. I've got X and P of X there. The first thing I want to note about this game in particular is that what value I'm going to be keeping track of here. So what's the expected profit? So I want to focus on X being profit. So what I make from the game, not what I win from the game. So looking at this, what are your options for the dice? It's 1, 2, 3, 4, 5, and then 6. So that's what you'd win if you rolled those. But you also have to pay $3 to play. So not all of these are going to come out positive. Yeah? So actually for the first X, it's a -2. Then I'm going to deal with a -1. Here you make 0. And then you make $1, $2, and then $3. I'm hoping this makes sense to y'all when you look at it. Because otherwise, oh boy. Okay. Oh no. My phone is making a ton of noise. I'm going to pause this for a second. Okay, sorry about that. So probability, so what are your chances of getting like a 1, a 2, a 3? There's 6 options, so it's 1 out of 6, which we're going to round to 0.167. So I'm going to be using, say 7 and write 3 for fun. I'm going to be using this rounded value to do this one in particular. I think 3 places should be enough to keep me right about accurate. I'm hoping you can't hear my cat meowing, because she would really like it if I would let her in this room right now for her to harass me the entire time. Anyway, she's also sticking her paws under the door. Good times. So since it's a nice fair dice, everything is equally likely to be chosen, so all my probabilities happen to be the same here. But never everything is created equal here, so notice I have a chance of losing some money on this game. So when you play at a casino, you also have to remember you have to pay to play, so that's why some of our values are negative. Alright, so first up, I gotta do X times P of X. So what I'm going to be doing here is taking like -2 and multiplying it by, this is not going to fit. I got to take -2 times 1.67, or sorry, 0.167, which will come out negative 0.33. And then I take negative 1 times, 0.167, so that'll come out negative 0.167 because, well, you know. You know what happens when you multiply by 1. Oh, 0 times stuff. That's easy. 1 times stuff again. No shocker there. Good times. Oh, 2 times stuff. So now we're going to double it. This is where things start to get interesting. 0.333. And then, oh no. I'm going to have to pause for a second and fix all these scales. Okay, sorry about that. 0, come on. You're on. 0.501. Okay, so I've got my first stage done. So I now need to do the expected value, which we know is the mean, the typical value, and that's by summing up this column right here. So we got to add those all together. So you'll notice you'll get some cancellation here because these values are the same, these values are the same, and these are negative. So not a big shocker. When you sum this all up, you get 51, which I'm actually going to round again because I'm going to try to make this fit. I'm going to call it 50 cents. This is money, so we're good. So on average, if you play, your long run chances of what you're going to get on average is 50 cents. So on average, you should make 50 cents if you play this game a lot. Long run average. On average. Not like every time you play, because you can't physically get 50 cents. Okay, I think we get this. All right, we got to do some subtraction now, because I got to do my standard deviation. So my first step is x minus my mean. So I'm going to subtract 50 cents from all my x's back here. So I got to do $2 minus 50 cents. That'll give me a negative 250. I'm going to do $1 minus 50 cents. That'll give me a negative 150. 0 minus 50 will give me just 50. 1 minus 50 will also, oh wait, negative 50. I almost forgot that. No, it'll also give me 50. I forgot that when you do 0 minus something, it comes out negative. Schwoops. Who teaches math? This chick. I don't know. At some point, this subtraction gets boring. All right. Now we got to square it. Time to square the things. X minus e of x squared. Oh boy. So remember earlier in the semester I was like, make sure you get a calculator you know how to use. This is where you use it. So now I'm just, oh no. I'm opening the support assistant in the middle of this video for some reason. And now you know the name of my printer is Printachew, so that's fun. Embarrassment. So I'm going to be taking this column right here, and I'm just going to square it. So I'm going to take all these values and square them. When you do that, you're going to get all positives, because remember, squaring makes everything positive. Who doesn't like to be positive? And these are easy because they're the same values. 225s. You're getting lots of 25s because that 0.5, you know. And oh, some 25s. Woohoo! I thought I muted that. Okay. I'm really hoping that this doesn't pick up on the video. Shh. All right, last but not leastly, thing I just did. Well, it's actually not last. You still have to do all add them up and then do some roots. All right, multiply by the probability. So I can go all the way back here to the probability, multiply it by this guy, put it right there. So I'm doing the 1/6 times the 6.25. When you do that, you get 1.044. All right, and then I'm doing 0.167 times 2.25. Okay. Palm rejection is not working today. 0.376. So what's nice is you know these bottom ones now because they're the same values. This does not always happen, ladies and gentlemen. 0.042, 0.042. And that's for me doing the 1/6 of 0.25. All right. Last up, you got to add this all up and then take the square root. So sigma is going to be the square root of the sum of this column. Which if you add up that whole column, you get 2.923. You do the square root, and you get 1.71. So on average, I'll make 50 cents with a standard deviation of just over a dollar 71 is specifically. So what's interesting about this is it kind of makes sense too. Like if you look at the spread around 50 cents would be about here. And then if you go like a dollar 70 in each direction, you pretty much get all of the data except for the two guys on the end. So it makes sense that this would describe the spread or average distance from the mean because on average, that's about how far away you are. All right, so that's as far as you need to get in your notes before you can move on to doing the assignment because all you're going to do is a couple of these guys for me. Oh, look, a binomial. That's fun. Yep, we'll worry about that for next time. Okay, I hope you have a wonderful day, and if you have any questions, please don't be afraid to ask. I will be available over email, and I will have office hours on Thursday, so, stop on by should you need me. Bye.